Hi, folks. Today we're going to talk about calculus. In particular, we're going to talk about limits. And so let's see what we can do. So calculus at its core is the study of how things move, grow, or otherwise change. It can model physical objects and how they move or change. It can model populations from ecology and how they relate to one another. Anything from economics to humanities, if there is some form of change, we can use calculus to model it. Now, again, there is no expectation that people in here have done calculus before. All that's expected is algebra 2 and some understanding of functions. Don't be afraid of calculus. We're not going to go in depth and do an entire calculus course in 30 minutes. We're just going to be introducing some of the core philosophies so that if you ever encounter a situation where you might be dealing with movements and change, you'll have some kind of intuition related to it. Calculus is in many ways a deep dive into functions, and it's often considered a first course in analysis. And so analysis is the study of functions, in particular related to continuity, continuous functions, curvature, measurement, and sequences. When we think of analytic geometry, the graphing we were doing, well, analytic geometry is just a cross between analysis and geometry. That's what it is. Real analysis studies real valued functions. Complex analysis studies complex valued functions. And functional analysis studies more complicated sets and structures. Calculus is largely computational introduction to these fields. And so when you think about what Calculus 1 and Calculus 2 are, they're really just the computational side of analysis. And so it's all about how can we measure rates of changes of things? And well, if we know a rate of change, how can we figure out what the original function is? That's the majority of calculus. Calculus 3 then applies it to vectors and higher dimensions, but it's all just about rates of change. How do things move, grow, and otherwise change? Before we jump into stuff, let's talk about why we need calculus. And to do that, we're going to go and talk about the paradoxes of Zeno and Aristotle. And so Zeno of Elea was an early Greek mathematician, and he's credited with some of the earliest calculus ideas. He came up with a series of paradoxes, which at the time seemed impossible. And using Euclidean geometry, they really are pretty much impossible to figure out. Euclidean geometry is static. It doesn't deal with moving things very well. And so the understanding of geometry and numbers needed to fully understand these paradoxes wouldn't catch up for a couple thousand years when Newton and Leibniz ended up figuring it out. Zeno gave us 3 classical examples, and Aristotle gave 3 additional paradoxes. They actually gave a lot more, but we're going to focus on these 6 in particular. The first one, Atalanta. And so Atalanta is a famed athlete of ancient Greece. To complete a foot race, she must first reach the halfway point. Well, before that, she has to reach the halfway point of that halfway point. Before that, she must reach the halfway point of that halfway point of the halfway point. In total, there's going to be an infinite number of positions that Atalanta must reach before she can reach the end of the race. How is it possible for her to reach an infinite number of locations? Is it just impossible for her to complete the race? And so that's the first paradox. Achilles is a very similar one. So Achilles and the tortoise. Consider a race between Achilles and a tortoise, where the tortoise is given a substantial head start. As Achilles races towards the tortoise, Achilles is going to reach the starting location of the tortoise, and the tortoise will still be ahead of him. Well, if they keep going, Achilles is going to reach that new position of the tortoise, and the tortoise will still be ahead. And well, if this continues, Achilles will continue to reach the previous position of the tortoise, and the tortoise will always be ahead. If this is the case, is it then impossible for Achilles to ever pass the tortoise? There's going to be an infinite number of positions where the tortoise is ahead of Achilles. How is it that Achilles can reach all infinite positions? The arrow paradox is another one, which is kind of similar idea. It deals with the idea of motion. And so consider an arrow shot through the air. As it moves through the air, it will go through a number of positions. But at any of these positions, at any fixed time, the arrow will appear motionless. In modern context, think of taking a picture. There's no picture or there's no motion when you take a picture of something, right? There might be a little blur, but you're not seeing how it's moving in space. It's a still image. Well, since the arrow is motionless at every point, how is it possible for the arrow to ever reach its target? It's just a bunch of motionless positions, right? So how is it moving if it is motionless? Another paradox is the paradox of the heap, or the Sorites paradox. A heap is a term used to describe a large quantity of something. And so if you have 10,000 grains of sand, that's a heap of sand. If you take 1 grain away, it is still a heap of sand. If you take 1 grain away, it is still a heap of sand. If you continue doing this, eventually you're only going to have 1 grain of sand. So is 1 grain of sand a heap of sand? Well, obviously not, but where's the fault in the logic here? The next one is the paradox of the moving rows, and this one's a little bit more complicated. And so consider 3 rows. We're going to have row A, row B, and row C. Row A is going to stay still. Row B is going to move 1 position to the right, and row C is going to move 1 position to the left. Well, after this motion, from the perspective of person A or a person in row A, it will look like the row has moved 1 position. But for people in B and C, well, B is going to look at C and see that they've moved 2 positions towards them, whereas B will have moved 2 positions towards C. Note here, we've moved 2 positions to the right from the perspective of C. This implies that any speed can be doubled with the right perspective. And so when we start thinking about how things are moving and how fast things are going, it's all relative, which, ends up leading to ideas of relativity down the road. Oh, the next one's weird. The paradox of the wheel. Consider a wheel with a blue circle around the edge and a red circle halfway between the center and the edge of the wheel. After rolling the wheel a full revolution, the path of the bottom of the tire will match the circumference of the blue circle. And so this blue line down here is going to be 1 circumference of the circle. The red circle will also have done 1 revolution. And so the red circle, it only went around 1 time. But in doing 1 revolution, it traveled the exact same distance. And so in this case, the red circle ended up going double its revolution. How is it possible for a circle to do a single revolution, but end up going double the distance of that revolution? And so these paradoxes, they didn't really have the tools to understand them at the time. I mean, they had some idea that something wasn't quite working, but they didn't have the ideas to figure out why these things were wrong. Euclidean geometry was all about static or unmoving objects, and there wasn't a good way to model how things are moving. You really needed analytic geometry in order to do that. We needed to be able to come up with some new way of describing motion. With the language of analytic geometry, there were 3 big mathematical concepts we needed to explain away these paradoxes. We needed sequences, and in particular, we needed a way to understand infinity. We need limits, which gives us a way of understanding closeness. And then we need continuity, which gives us a way of understanding connectedness. These 3 things are kind of the underlying principles of calculus, the 3 things which lead to us being able to understand how things move, grow, or otherwise change. And so today we're going to focus on these 3 concepts and see if we can understand the idea of sequences, limits, and continuity. And so let's begin with sequences and summations. Can we add an infinite number of objects? I mean, one of the issues that we had was we were saying that we had to reach an infinite number of positions in order to overtake a turtle. Is that possible? Well, let's see. And so when we first introduced the idea of patterns, we did so in the language of sequences. A sequence is a listing of numbers which goes on forever. Technically, from a set theory perspective, they don't even need to be numbers. What's special about them is they give us a way to understand long-term behavior for infinitely described objects. And this idea of infinity is very, very important. What does it mean to be infinite? We've talked about infinity and infinite things in the past, but now let's explore it from a sequence perspective. And so one frequent application of sequences is adding up terms in a sequence. Is it possible to add together an infinite number of numbers? Or will you just always get infinity? And so this is something we need to think about. And to begin with, let's talk about Gauss's problem. And so Gauss was a prodigious mathematician, and he was notoriously a bad student in his youth. As punishment, he was sent to the corner and asked to add up all the numbers from 1 to 100. It took him a couple minutes, and he had the answer. As further punishment, he was asked to add up all of the numbers from 1 to 1,000,000. It took him seconds. And so the question is, how did he get it so fast? And in order to better understand this problem, we're going to need to introduce some new symbols. And so when adding up a small number of objects, you can just combine them from left to right and you get an answer. You don't have to worry too much about it. For sums which involve more terms, like if we are adding up 1,000,000 terms, we're going to need a new notation for that. And that's where sigma notation comes in. And this is our sigma notation. It uses the Greek letter sigma. You can see that we have a few terms around it. The sigma notation, sigma just says we are adding up a whole bunch of things that look like whatever the thing is to the right. We then have a lower limit and an upper limit. And so the lower limit is saying, what is our variable that we're dealing with and where are we starting? The upper limit is saying, where do we stop? And then the argument is saying, what do these things look like? And so here's a simple example. If we are adding up things from I equals 1 to n, and the thing is a sub I, then we would be saying a sub 1 plus a sub 2 all of the way out through a sub n. Note in our final summation here, we don't actually have the I term because I was equal to these values. And so this is our notation we're going to be playing with. Here's a couple examples. And so suppose we want to add the first 5 perfect squares. We can write it like this. This would be the sum from k equals 1 to 5 of k squared. And so we would plug in 1, we'd get 1 squared, 2, 2 squared, 3, 3 squared, 4, 4 squared, and then 5 for 5 squared. And then we're going to add them all together. And so this summation from 1 to 5 of k squared is just 1 squared plus 2 squared plus 3 squared plus 4 squared plus 5 squared. We can do the math, we get 55. In the case of Gauss, he was tasked with adding up the first 100 numbers. And so we could write that like this. K equals 1 to 100 of k. And so the sequence 1, 2, 3, and so on is an arithmetic sequence or an arithmetic sequence. And we are adding up the values. It would likely be overly tedious to do this by hand, but I mean, if you want to, you can. Go grab a calculator, see if you can do it. Or don't. So we need another strategy. Here's how Gauss approached it. And so in adding 1 through 100, what Gauss recognized is that he could pair the first and last numbers together and always get 101. And so 1 plus 100 is 101. 2 plus 99 is 101. 3 plus 98 is 101. All the way through 50 plus 51. And so he has 50 pairs of 101. Well, that's multiplication at that point. And so 50 times 101 gives us 5,050. For the next example, adding up the numbers 1 through 1,000,000, It's the same exact process. You would do the 1 plus the 1 million, which would be 1,000,001. And then you would multiply by how many there would be, which would be 500,000, because they would meet right in the middle. And so 500,000 pairs of 1,000,001 gives 500,500,000,000. That's a very large number. In general, he found adding up the numbers from 1 to n would give you s equals n over 2 times n plus 1. And again, when we think about Gauss, this is an old story. Whether it's true or not, it's hard to say, but Gauss was definitely a recognized mathematician, and it would not be surprising if he got in trouble for stuff like this. So now we ask the value of the summation notation. Summation notation itself doesn't present the answers, but it does condense the questions, which can allow us to better analyze the problem. For example, is it possible to add an infinite number of values, or will you always get infinity? Well, this is where we need to start talking about infinity and what it means to add an infinite number of numbers. We call such an infinite summation a series, and it turns out they will often give finite answers. Not always, but sometimes. Here is one very weird example which pops up. 1 plus 2 plus 3 plus 4 plus 5 plus 6, all of the way out to infinity. What do you get when you add up the numbers from 1 to infinity? Well, it should be pretty obvious you're going to get infinity. The numbers are going to get very, very, very large. But there are some applications where it turns out we get that this infinite summation can be approximated by -1/12. And there's some interesting reasons behind it. And if you want, you can watch a video on it. We won't go into it here. But there are some very weird things that can start to happen when we start talking about infinite summations. Let's start with nice stuff, though, because I like nice stuff. And so we're going to start with geometric series, in particular, a unit square. And so let's think of a 1 by 1 square. If we cut the square in half, then we're going to have an area of 1/2. If we cut what's left in half, we're going to get an area of 1/4. If we cut what's left in half, we're going to get an area of 1/8. Cutting that in half, we get an area of 1/16. And we can continue this forever and ever and ever. Well, when we think about what this would represent as a series, as an infinite summation, we are saying that the sum of values of the form 1 over 2 to the k, so 1 over 2 to the 1, 1 over 2 to the 2, 1 over 2 to the 3, and so on, is going to give us an area of 1. Because if we do this infinitely, we are going to get this entire region covered. And so there we have it. We can add an infinite number of things and get a finite value. The values just have to get small enough, quick enough. A general geometric sequence can be written in the form AR to the n minus 1. So let's do a little bit more with geometric sequences. Where A is your starting value, R is your multiplier, and n represents the nth term in the sequence. We need the n minus 1 in the exponent because the first term should always, or should just be your A value, right? Making it n minus 1 gets rid of the R multiplier for the first term. And so if we have 3, 6, 12, 24, this is a geometric sequence of the form 3 times 2 to the n minus 1. If we wish to add up the first 5 terms, we could say it's going to go from k equals 1 to 5 of 3 times 2 to the k minus 1. That'd be 3 plus 6 plus 12 plus 24 plus 48 is 93. And we can just do that one by hand. What if we had more numbers, though? What if we had an infinite number of numbers? What would we do then? And so consider the example from before, but suppose we wish to add the first 20 terms. Instead of adding all 20 terms involving very large numbers, it might be nice to come up with a shortcut. We want a formula that will give us this answer every single time. And the neat thing about geometric sequences is we can do this. In general, we can't for other sequences, but for geometric sequences, we can. And so here's how we do it. Consider adding the first n terms of a geometric sequence. And so we would say, let's let that be S. S will be the sum from k equals 1 to n of AR to the n minus 1. And we can list out the terms. At 1, we're going to get A. Then we're going to get AR. Then AR squared and AR cubed, all of the way out until our last one is going to be AR to the n minus 1. Oh, and this n here, there's a typo. This n should really be a k. So AR to the k minus 1. AR to the k minus 1. Those typos always get me in trouble. Down here as well, AR to the k minus 1. And so now let's consider what happens if we multiply each term by r. Well, we'll get r times the summation, which is really just taking all of these terms and multiplying them by r. Well, if we subtract these, the a would be left over, but AR minus AR would cancel. AR squared minus AR squared would cancel. All of these terms would cancel except for our last one, AR to the n. And so we get S minus RS is equal to A minus AR to the n. Factoring out the S and dividing both sides by 1 minus R, we get that S, so the summation of this thing, where that's a K, not an N, that's going to drive me crazy, is equal to A times 1 minus R to the N, because we could factor the A out on top, over 1 minus R. This is a formula which will always tell us the sum of a geometric series. Consider the example from before. And so the sum from k equals 1 to 20 of 3 times 2 to the k minus 1. Oh, I have it here too, I swear. If S is equal to the sum from k equals 1 to n of AR to the k minus 1, it's going to be represented by this formula, which we just proved. Well, A is 3, R is 2, N is 20. We can plug that into our formula. We end up getting 3,145,725. And so if we add the first 20 terms of this sequence, we end up getting this number. We now have a way to add up any number of elements in a geometric sequence. Well, what if we add up an infinite number of them? And I can see already that I am going to have that K issue again. And so what if we wish to add up an infinite number of terms of the sequence AR to the n minus 1? Well, the first thing to note is that R must be a fraction between -1 and 1, because otherwise the terms are going to grow infinitely big. In our first example, we did 1/2 plus 1/4 plus all of the way out, and we had no problems because R was 1/2, and the terms got infinitely small. For the finite case, we had this formula. If we continue with this equation to infinity and assume R is between -1 and 1, then the R to the n will get infinitely small. And so this R to the n term will disappear at infinity, which means that this summation from k equals 1 to infinity of AR to the k minus 1 is equal to A over 1 minus R. This is a very nice formula, which I messed up. So here's some examples. If you like, give them a shot. The first one is saying add up the first 20 terms of this sequence. The second one is saying add up the first infinite, or add up all of the terms in this sequence. And so for the first case, we're using the formula for finite, and A is 3, R is 1/3, and N is 20. We plug that in here. We end up getting, goodness, a very large fraction, which ends up being roughly equal to 4.49999, and it goes on for a while. If instead we said, let's let A equal 3 and R be 1/3, and we added up the infinite number, we end up getting 4.5 out of this thing. As we can see, the sum of the first 20 terms was very close to the sum of the infinite number of terms. And that's generally going to be the case. For non-geometric series, we can't get away with doing this. So for geometric series, we have a nice formula. In general, it is not that easy to determine if an infinite sequence converges to a finite number or not. It's even harder to find the actual value. So in Calculus 2, you learn techniques to determine if a series is converging or going off to infinity, but you don't actually learn techniques to solve them. We can't actually solve what the summations are in a general way. Here's two quick examples. Let's suppose that we are adding up the fractions of the form 1 over k. So 1 over 1 plus 1 over 2 plus 1 over 3 plus 1 over 4 plus 1 over 5, and so on. It turns out we can prove that this does not give a finite value. This infinite summation is going to go off to infinity. For the second one, it's the same idea, but now we're squaring it. So this would be 1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared plus 1 over 4 squared. This one actually does converge, but it converges to pi squared over 6. This is a weird little proof, and in order to prove it, you need some higher level calculus. We need to have a Taylor expansion. We need to actually rewrite it as a product. There's some really fun stuff that happens in trying to prove that this summation is equal to pi squared over 6. For our purposes, we're not going to go that far. We just need to understand that we can add an infinite number of things, and we can get a finite value. We need to have an understanding of infinity. And now we have an understanding of infinity. And so let's talk about limits. And so what does it mean to be close? That's really what a limit is all about. And so a limit answers the question, what number am I approaching? It gives us a way to understand what it means to be close to a number. In the case of the geometric series, when we added 20 terms, we could see what number we were approaching. Limits formalizes this idea. And so when we deal with limits, we're usually interested in limits of functions or sequences. Often we focus more on functions than sequences, to be honest with you. But sequences are just functions on the natural numbers, and so they're very similar. There are two primary types of limits. There are limits at finite values, which ask what value a function is getting close to near some value. And so what y value are we getting close to near an x value? If a function is undefined, but it looks like it should be some value, what is that value that it looks like it should be? That's what a limit at a finite value is. Limits at infinity ask for the long-term behavior of a function or sequence. And so as you go out to larger and larger numbers, what does it seem like the function is approaching? That's what a limit at infinity is. And let's play with this idea and see if we can understand it. And so we're going to start with a limit at a finite value. And so let's consider this function. F of x equals x squared minus 4 over x minus 2. And we're going to talk about what's happening around x equals 2. Well, if we try and plug 2 in, bad stuff happens. We're going to get 0 divided by 0, which is not defined. We're not allowed to divide by 0. That was one of our things that we discovered when we were talking about binary operations. But if we look at the graph, we can see that the graph is a line, and it's a line which just has a hole right there. While the value doesn't exist, x values near 2 really look like they are approaching 4. And so this idea that as you're getting close to 2 in the x direction, our y values are looking really close to 4 is what a limit is all about. And so we would say that the limit as x approaches 2 is 4. And we could write that in this format. The limit as x goes to 2 of this function is equal to 4. As we're getting close to 2 in the x direction, we are getting close to 4 in the y direction. That's all the limits are. Limits are just saying, hey, what should it be? Limits at finite values, here's an example. And so consider this function, f of x is equal to x squared for x less than 2, and square root of x for x greater than or equal to 2. Here's what the graph looks like. If you notice, as we're approaching 2 in this case, from the left, it's approaching one thing, and from the right, it's approaching a different thing. To denote that, we would say that we have a left-hand limit and a right-hand limit. And so the left-hand limit is what does it look like you're approaching from the left? And in this case, from the left, it looks like we're approaching 4. From the right, well, it looks like we're approaching 0. And so our limit from the left is 4, and our limit from the right is 0. We would say that the limit itself exists if those two things were the same value. If they're not, we can just look at the left and right hand. It's okay. And so one approach to finding limits is to utilize algebraic properties. If we don't have the graph, or if the graph isn't really clear, we can always go back to algebra. And so here's an example. Consider the function f of x equals the square root of x minus 1 over x minus 1 at x equals 1. Well, again, if you plug 1 in, you're going to get 0 over 0, which is undefined. But what we can do is we can actually clean this up by using the conjugate. Remember in Algebra 2, the conjugate is a way to move a radical to the top or to the bottom. And in this case, we would want to move it to the bottom. And so we could multiply by square root of x plus 1 over square root of x plus 1. And doing that, we're going to get a fairly nice equation. We're going to get the x minus 1 over x minus 1 cancels, and we're left with 1 over square root of x plus 1. Well, 1 over square root of x plus 1, we could evaluate that at 1. And plugging 1 into this equation gives us 1 over 1 plus 1, which is 1/2. And so this is a way of determining what this value would be. At 1, we can't evaluate this, but if we do a little bit of algebra and try and simplify this, we can get an expression which we could evaluate at 1. And so evaluating this at 1, we get that the limit as x goes to 1 of this function is 1/2. Sometimes we can't do algebra. In that case, we have to use some other approach. In this case, the function is x sine of 100 over 5th root of x at x equals 0. This is a very weird looking function. And if we want to figure out what's happening at x equals 0, well, we can't just plug 0 in. If we plug 0 in, we're going to get 0 in a denominator, and we can't have 0 in a denominator. But when we look at the graph, we can see that this function is bounded. It looks like it's bounded between the lines y equals x and y equals negative x. And it's going to be bounded that way all the way throughout. And so at 0, that would mean that it's going to be bounded between 0 and 0. The only number between 0 and 0 is 0. And so we can kind of squeeze this graph between those two other functions and see that the limit as we go to 0 is going to be 0. That's an analytic approach. We're basically using the structure of functions themselves to try and figure out what limits are. Now, limits at infinity work a little bit different. Instead of looking at a particular value and saying what happens near that value, we're saying what happens if you get to a really, really large number. And the thing about large numbers is any large number you can pick, someone can pick a larger number. And so we want to figure out what the long-term behavior is going to be. In this case, this function is 3x to the 4th plus 100x cubed natural log of x over x squared times 10e to the negative x minus 7x squared. In Calculus 1, you learn techniques to try and figure this out. What is the value that it's going to be approaching in the long term? From here, it's hard to tell. I mean, only going out to 21, it might keep going up, it might not. But using the tools of Calculus 1, we can actually ask what terms in this ratio actually matter. And it turns out the only terms that matter are the 3 and the negative 7. We won't go into why that is, but the long-term behavior of this is that it's going to approach negative 3/7. And we can use calculus to figure that out. The last piece of the puzzle we need is continuity. Continuity, much like graph theory, is all about what it means to be connected. And so continuity is a way to determining if a function is connected or not. We often say a function is continuous if it can be drawn without lifting a pencil. The example to the right is continuous except at x equals 2. At x equals 2, we would say it is discontinuous because it jumps from one value to another value. Formally, we say that a function is continuous at a point if the limit and function value at that point are the same. And so if the limit as x goes to a of f of x is equal to f of a, then the limit, or then the function is continuous at a. For our purposes, we're just going to look at the basics though. And so we have a few different types of discontinuities that are interesting. One is a point discontinuity, which we've already seen. A point discontinuity just means that you've got some curve and there's just a point which has been removed. Well, if there's a point which has been removed, we can figure out what the limit is fairly easily. But this is an example of where it's discontinuous. A jump discontinuity is where the function seems to be doing one thing at one point, and then it jumps to some other point. And so in this case, at x equals 2, we have a jump discontinuity. Goes from doing one thing or being one function to being a completely different function. There's also infinite discontinuities. If you have a vertical asymptote, whether it goes up and then comes back down, or it goes up and then comes back from the bottom, at this point where it hits infinity, we're going to have a discontinuity, and we call that an infinite discontinuity. Final thoughts. And so we've talked about a lot of things today. And so the ancients did not have the tools needed to understand motion at a deep level. For that, we really needed analytic geometry. We needed some way to visualize how things are changing. Once we had the idea of functions and graphing, the pieces started to come together. We could understand infinity, both what does it mean to be infinitely large and what does it mean to be infinitely small. In the case of infinitely small, that's how we understand closeness. And we can understand what it means to be close to a value. That's what a limit is all about. We could then also understand what it means to be connected through the idea of continuity. Using these tools, we're able to describe motion. And we did so by defining the rate of change of a function, which we call the derivative. All that the derivative is just the slope of a function. And that'll be the next thing we explore next time. With that, I'll let you get to work exploring where you find limits, continuity, and infinity in the real world. Good luck, folks.